So for the most part, we're going to be reviewing some basic integration techniques here. Typically, you want to start out to see if you can just basically integrate it, essentially using the power rule. However, if you have variables times variables or variables divided by variables, that doesn't work. So then the next thing you should try is use substitution. However, use substitution doesn't always work. It often does, but not always. So if those two options don't work for you, then you want to consider some of these others. So if you have a situation like this here, you just want to FOIL that out. In other words, you'd want to expand it. If you have this, you could do longhand division. If you did longhand division, you would essentially get this. Or you could go ahead and just write it as two separate fractions. Now, you could complete the square. That's not too often used that I'm aware of. Here's your longhand division. Typically, if the top has a higher power or same power, you do longhand division. Um, you could go ahead and do special numerators, essentially adding 0, and then separating it up. That, in my opinion, rarely is used. You may want to go ahead and do a trig identity, substitute them, or you might have to do a conjugate of one of your trig identities. So the ones that are highlighted in yellow are frequently used. This bottom one is occasionally used. These other two that are underlined in blue are rarely used, but are still available options for you. So let's consider this. Now, this particular problem does not work for use substitution, and it doesn't work with anything that we've discussed up to this point. So you want to go ahead and look at your integration table. The integration table is on your class website, so go ahead and look at that. That's the full table. Part of the table is displayed right here. So some of these things you know, like the integration of e to the u is e to the u plus c, or integration of cosine is sine plus c, and so on. Some of them are not as obvious as you get down here farther, and if you get farther into the table, they're not nearly as obvious. Basically, what happens is you take the derivative of something, you end up with a formula, and then your integration table is looking at all those patterns we've seen in the past and using those to work backwards. So that's what your integration table is about. So for the most part, I want you to go ahead and look at this right here and see if you can look through your table to see which one of the formulas in your table may work. Now, knowing that you can go ahead and take this timesing by 4 and put it in front, so you want to essentially look for something like this in your table. Well, if you do that, you eventually find something that works. Formula 23 that looks like this. You have something squared here plus something squared here in the bottom. Now, keep in mind, A is always referring to a number. So in this case, A would be your 3. U is always referring to your variable. In this case, it's X. So this is what we want to use. So all we're going to do is replace this right here with this using our formula. So when we do that, we replace our A's with 3's, replace our U with X, and we get this here. So what I would do at the end is basically take my 4 times only 1/3 in front and then leave it like that. That's what I would write. Now, as a side note, you might be wondering, well, where does this come from? Well, consider this. If you started out with, we'll switch it to this. And if you wanted to start out with, let's see, theta is equal to the tangent inverse of u over a. Remember, tangent inverse is the same thing as arc tangent. So if you wanted to do the derivative of this, well, what you would do is essentially do it like we've done before. You'd want to just get it into terms of tangent because you know how to do the derivative of tangent. So do the tangent of each side, you get this. Derivative of the left side, derivative of the right side. Remember, this is u times 1 over a, so that's why there's a 1 over a here. Then you'd want to go ahead and when we are looking for the derivative of this, it would be d theta du, get d theta du by itself. So in other words, you'd take your secant squared to the other side by dividing, but remember, dividing by this would be the same as multiplying by the reciprocal. So that's where we get this. So we have our 1 over a in front. But now we're going to go ahead and draw a triangle related to this. Remember from SOHCAHTOA that tangent is opposite over adjacent, so that's why we have these two. And now you can use your Pythagorean theorem to get your hypotenuse. So instead of writing cosine squared here, we go to our triangle and go our cosine, which is adjacent over our hypotenuse. So we go adjacent over hypotenuse and then still square that. Well, we could square the top, square the bottom, and we would get this. Remembering you get an a squared on top, but you have this a in the bottom, so that's why it just simplifies to an a to the first in the top. So what we have here is similar to what we had. So that's why this formula works, is it comes from taking the derivative of your inverse tangent. And that's the way all these formulas in your table work. It comes from looking at something that we took the derivative of. So when you're looking at doing your integrating, you try to do your normal integration first. Then you try to, all those other techniques that we talked about back here on this slide here. If none of them work, then you look through your table to see if there's any of these formulas that will work for your problem. So let's consider this. Now here, you might be looking at this going, I don't know, normal integration doesn't work. But what do I consider? Well, a lot of times you want to try u. In this case, u could either be your cotangent, x, or it could be your natural log. Those would be your two primary choices. Could u also be your sine? Yes, but if you do the derivative of sine, you get cosine, and that doesn't show up in the rest of your problem. So as you look here, if you considered u being this, if you did your derivative of u, you get a du is equal to the derivative of a negative cosecant squared x dx. But that doesn't show up in the rest of our problem. However, let's consider u being this. Well, remember when you do the derivative of natural log, you go 1 over what's after your natural log times the derivative of the inside, which is cosine. Well, you know cosine over sine is a cotangent. And hey, we have a cotangent showing up in our problem. So yes, u does work on this problem. So essentially, we're going to let u be this, and then du is our cotangent. So always try to do your normal integration, check for u, try those other techniques, and then always go to your table as a last resort. So basically, if we substitute stuff in, this is your du, this is natural log of u, or is just u. So integrating this is really pretty easy. We just get a 1/2 u squared plus c, substitute in what u is, and then we're done. So once again, always check to see if you can do normal integration, check to see if u works. I'll only use your table as a last resort. So here, well, looking at this problem, you know you could always pull your 4 in front. You have an x squared over an x squared plus 9. A lot of times if you have a situation like that, you want to just do your longhand division. Well, if you do longhand division, you would get a 4 plus, and then your remainder would be a 36 over what you were dividing by. Well, you could just go ahead and do the integral of the 4 minus the integral of that fraction. Well, the integral of 4 is pretty easy to do, you know. Now, we did not do anything special on this first part. However, over here, you should realize that this matches up with what we did on that first problem with arctangent. So sometimes when you're doing these problems, you'll be able to do the integral of part of your problem quite easily, and you'll only need to use your formulas from your table on part of it, and that's what we're doing here. So just be aware that sometimes you have to do that. So substituting in what u is, which is x, and a, which is 3, because this is a 3 squared for your 9, we end up getting this. So in other words, 36 times a third is 12. So you get your 4x from the beginning minus a 12 arctangent of pi, or x over 3 plus c. So just be aware, sometimes you have to use your table only on part of the problem.